Hey folks, welcome to this episode on writing equations. So what is a chemical equation? Well, it's just a written representation of an observed chemical reaction. We can't actually see what's happening at the molecular level, but we try to represent it through the use of equations. We have two main ones that we use, word equations and skeleton equations. Words obviously use the names and the words to represent the chemicals, while skeleton equations use the chemical formulas. The skeleton equation, however, is usually seen as a balanced chemical equation. So that means that we're taking into account the law of conservation of mass. On the bottom here, we see an example of both of them. We have our word equation, which just says carbon dioxide to form carbon dioxide. In our skeleton equation, we are seeing that we have the individual elements and the compounds, but we also include things like the states. Now, these obviously offer a little bit more direct information. You can see how many atoms there are instead of trying to figure them out through this kind of equation, but that, needless to say, you can still find that out there. The main thing is that the skeleton equations or the balanced equations give you the states, while the word equations do not. So when we burn methane gas, we burn in the presence of oxygen to produce carbon dioxide and water. Now, this is what happens at the reaction at the molecular level, but we don't actually really see that. And even so, we rarely have a single molecule reacting with other individual molecules. We usually see moles of something reacting, and that's something that we can control as chemists, where we can figure out how many moles we have reacting, something a little bit more tangible for us. So mole is just a unit of measurements. All it is 6.02 times 10 to the 23rd of whatever we're measuring. So in this case, when we have 1 mole of methane gas, it means we have 6.02 times 10 to the 23 molecules of methane reacting with 2 moles of oxygen, etc., etc. So that is our descriptive observations. We see that we have these individual things reacting. Our word equation is simply methane plus oxygen gives us carbon dioxide and water. And when we turn that into a skeleton equation, we can see that, again, we have the states. The one step further, which is going to be looking at it in a different lesson, is actually balancing these equations to make sure that we have proper law of conservation of mass and then that it's being met. So in this case, this is the first step in writing a word equation. And in this descriptive observation, we really want to look at what you're observing. Now, again, you can't observe it on the molecular level, but this is where your kind of knowledge of the chemical reactions and what should be coming out of it will apply. This usually applies when we're doing our pre-labs or our pre-investigations. And this is the kind of stuff that you should be looking at. What are we reacting and what are the potential outcomes? There could be some factors that are unknown. For example, if you're burning anything in air, it might not only burn in oxygen, but it also might react with the nitrogen in the air. So there are some unforeseen products that you might not think about. But for the most part, you should be looking at what substances are involved, what are the things that are produced, and what are their possible physical states. So in this case, I grabbed this from a demonstration on YouTube, and the acknowledgement is in the back. In this case, this gentleman was adding a piece of aluminum into sulfuric acid, which is found here. Now, as they put it in, initially there was not a huge reaction, but after a few moments, you saw that there was all these bubbles being created. So in doing this lab, first thing we'd want to do is prepare for the lab and say, okay, well, we're adding aluminum to sulfuric acid. What kind of reaction is it, the type of reaction? And from that, can we predict our products? Now, from this, you should be able to find out a couple things and hopefully predict the products. So what we found is that through this reaction, we should form hydrogen gas and a aluminum sulfate solution. You might not necessarily know the states right away, but you should figure out what compounds are going to be created. So if you know what is reacting, here are our substances. So we have aluminum and sulfuric acid, and what's going to be produced, hydrogen gas and aluminum sulfate. We can come up with a descriptive observation of what's actually happening. Now, to go into word equations, we should take our observations and pick out the important things. So you can either start with your descriptive observations that you collected or that was maybe given to you by a partner or whatnot from a lab. Sometimes you also might be given a chemical equation and asked to be converted. That's simply to see if you actually know what you're doing. But usually in the real world or in our labs, we're going to be starting out with one of these. So the main thing you want to do is first identify your reactants and your products, write down their names, and put plus signs between the individual reactants and products, and to separate the reactant side from the product side, you'll use an arrow. So if we look at this example over here, when again we have aluminum metal dissolves in an aqueous solution of sulfuric acid to form hydrogen bubbles and a solution of aluminum sulfate, well, first thing we have to do is figure out what are our reactants. Well, aluminum is dissolving in an aqueous solution of sulfuric acid. And the key word here is to form. So now we know that we're going from our reactants, which is on this side, to our products, which is going to be listed later. And what do we form? We form hydrogen gas and a solution of aluminum sulfate. So if we put this together, we have our aluminum, so aluminum plus our sulfuric acid. And this is going to be separated by an arrow. And here we have hydrogen gas. We have, well, it's just simply hydrogen plus aluminum sulfate. And that is our word equation. So in this case, what I'd like you to do is come up with a descriptive observation of what is happening here. Now, to give you a little background on this experiment, here we have a copper wire put into a solution that used to be clear and colorless. As the reaction occurred, we started getting these metal flakes, these flakes of silver on the copper, and the solution started to turn blue. So what we have here, and these descriptions are kind of showing what is happening. We have copper metal in a solution of silver nitrate, and in this case, the silver and the nitrate dissociate when in water, so they form silver ions and copper metal solid. And in this part over here, after the reaction, what we're seeing is that we are forming solid silver and copper 2+ ions. So in this case, copper 2 nitrate. So knowing that, try to come up with a descriptive observation and a word equation for this. So pause the video. We'll be back in a few moments and see what we can come up with in terms of this reaction here. So in this case, what we're seeing is that copper metal over here is reacting with this once clear and colorless solution of silver nitrate. So that's a copper and silver nitrate. Now copper is a metal, so we're kind of showing the states there, and an aqueous silver nitrate solution. So that means that silver nitrate has been dissolved in water to create this as a silver nitrate solution. And this produces copper 2 nitrate, so that forms the kind of blue solution here. It's the copper 2+ ion that gives it the blue color. And we're creating these silver metal flakes. These are these things over here, which look into these kind of like fingers over there. And so this is our descriptive observation. And again, this would only come by through looking at this and saying, okay, well, I have copper and silver nitrate reacting. What type of equation is it? Or what type of reaction can we see? And what are the possible products in this? Once we know that, we can come up with a descriptive observation, and then finally a word equation, which is copper plus silver nitrate gives us copper 2 nitrate and silver. Now going from word equations to skeleton equations, and a skeleton equation is just representing that chemical reaction in terms of chemical formulas instead of words, and we also include the states of these formulas. Now remember, ionic compounds, you'll frequently see these in the skeleton equations, and the way that we come up with the formula are through the cross-down method, and this allows for charge bouncing. So if you don't remember what the cross-down method is, or that doesn't seem familiar to you, let's just do an example here. So what's the formula of calcium nitrate? Well, we know that calcium is Ca, nitrate is NO3. The charge of calcium is, well, it's in the second group over here, so it's going to be 2+, and nitrate is 1-, and we cross-cross. So we get Ca bracket NO3 bracket 2. So that's how we figure out our formulas for our ionic compounds, and this helps us build our skeleton equations. So let's go back to this example. We have aluminum plus sulfuric acid to create hydrogen and aluminum sulfate. So the first thing is, let's figure out what the formula for aluminum is. That's very simple. It's a simple metal, so it's Al, and it says aluminum metal, so we're going to assume it's in the solid form. Plus, well, we have to figure out sulfuric acid. Sulfuric, remember that ending comes from 8. So it's going to be sulfate, which is SO4. And because it's an acid, it has to have hydrogens. This has a charge of 1+, and this has a charge of 2-, so cross-cross, and we get H2SO4. And this is going to be aqueous because it's a solution. Now, this forms hydrogen. Now, remember, hydrogen is a diatomic molecule, so it exists as H2. So H2, and it says hydrogen gas. So it's going to be H2 gas. Excuse me, not an arrow. We want a plus sign. Plus aluminum sulfate. So again, we have AlSO4. This has a charge of 3 plus because it's in the third group. This charge of 2 minus. Cross cross, and we get Al2 bracket SO4 bracket 3. And it says that it's a solution, so this is going to be aqueous. And there is our skeleton equation. So here's another example. Dissolved sodium hydroxide reacts with sulfuric acid, yielding aqueous sodium sulfate and liquid water. So first things first, our dissolved sodium hydroxide, so that's Na and OH. This has a charge of 1 plus because it's in group number 1. This is 1 minus from memory, cross cross, and we get NaOH, and it says dissolved sodium, so that means that it's dissolved in water, aqueous, plus sulfuric acid. So again, we need H for an acid, SO4 because it's going to be sulfate. 1 plus, we cross cross, and we get H2SO4, and again, that's going to be aqueous because it's an acid, yielding aqueous sodium sulfate. So sodium sulfate, we're going to need Na and SO4. Again, Na is 1 plus, it's in group number 1. Sulfate is 2 minus from memory. We cross cross, and we get Na2SO4, and that's again aqueous from our sentence, plus liquid water, so that's simply just H2O, and the state is liquid form. So there again, we have our skeleton equation. All right, so pause the video and try to convert the following skeleton equations, descriptive observations into skeleton equations. So pause the video, try your best, and unpause when you're ready to have the answers. Well, welcome back. Here are your answers. We have beryllium chloride, so we have Be having a charge of 2 plus, Cl have a charge of 1 minus, so we cross cross. Ag, remember that's one of those special ones. We have 1 plus and 1 minus for nitrate, so we cross out, we get AgNO3, again aqueous. Beryllium nitrate, again here we have 2 plus because it's in group 2, and we have 1 minus, so we cross and we get BeNO3 2 in brackets, and AgCl 1 plus and 1 minus, we get cross, we get AgCl. And it says powder here, so powder is in a solid format, so we're going to get a solid. Ethylene gas or ethene gas, C2H4, you're going to see obviously in gas, and it already gives you the formula for that, so that's pretty simple. Oxygen is diatomic, okay, diatomic, so that means it's going to exist as O2. Carbon dioxide is molecular, so remember that the prefixes give us the number of oxygen atoms. Now, because there's no prefix in front of carbon, that means there's going to be 1. Remember, we never use the mono prefix for the first name. So there was going to be 1 carbon and 2 oxygens because of the dioxide. Finally, water there. We don't have to add heat here because it's not an actual physical product. It's a type of energy. Some places will put plus energy over here, but in terms of our actual reactants and products, we don't need to include that there. Okay, now take a moment and pause the video again and try to convert these skeleton equations into word equations. Okay, so pause the video. When you come back, we'll have the answers for you. All right, so welcome back. Here are your answers. Potassium iodide plus lead-2 nitrate gives us lead-2 iodide and potassium nitrate. Now, how do I figure out that this was 2? Well, remember that to figure out the charge, we first have to figure out, well, this is a multivalent metal. It's one of those poor metals that has more than one valency. So we need to figure out what the charge is so that we can put it into Roman numerals. Now, the way that we did that is, again, we look at our formula here, PbNO3 2, and we upcross to put the charges on top of the metals and the nonmetals. The next step is to compare this charge of the nonmetal to the known charge of this nonmetal. Now, NO3 has a charge of 1 minus, so this is good. Now, if this is good, that means that this is, in fact, the charge of the metal, so it's lead-2 nitrate. Same thing for lead-2 iodide. I did the upcross, the charge, because there's no subscript. The subscript was 1. Here, the 2 on top. And again, I compared the charge of the iodine from the formula to the known charge of iodine. And when I looked on the periodic table, it was in group number 7, which means it gains 1 electron, making it -1 or 1 minus. This is good, so that means that is the actual charge of our metal, so we get lead-2 iodide. Barium carbonate, no tricks there. We get barium oxide and carbon. In this case, we have carbon dioxide. There's an extra D there. Okay, tricking you all. Okay, carbon dioxide. The only problem that we run into is, say for example, we have this ethylene gas again, we react it. And what we see is that we do not have equal mass on both sides. If we look at the mass on this side, on the left side, we have carbon. So each carbon weighs 12 grams per mole times 2, and we have 24 grams. Each hydrogen weighs 1 grams times 4. We have 4 of them. That's going to be 4. And we have oxygen. Each oxygen weighs 16 grams per mole times 2, and we get 32. So in this case, if I just do some quick math, I get 50, I get 60 grams, if I'm not mistaken. Let me just check my math. 12 times 2 is 24. 1 times 4 is 4, so that's 28. 30, 40, 50, 16 times 2, 32. So we have 60 grams on our left side. On our right side, we have 1 carbon. So that's 12 times 1 gives us 12. We have we have 2 oxygens. 16 times 2 is going to give us 32. So here we have 44 grams plus the mass of water. So here we have 1 times 2 gives us 2, and we have 16 times 1, and that gives us 16. So we have 18. So now what we have is we have 44 plus 18 because we're looking at the total mass on this right side over here. So we have 50, we have 62 grams. So we've gone from 60 to 62 grams. We couldn't just create mass like that. So what we're seeing here is that this equation doesn't allow or doesn't account for the law of conservation of mass. It doesn't fit because the law of conservation of mass says that both sides should have the same mass. And the only way that you can get same mass is by having the same amount of atoms on both sides. So clearly, this doesn't have the same amount of atoms. So what we're going to have to do is we're going to have to use a technique called balancing to figure that out. So that is going to be in the next couple lessons. We'll see you next time. Thank you for watching this episode. Take care, folks.